Hello again. So in a previous recording, I mentioned that I'm going to talk about Dijkstra algorithm in a separate recording. So here we are. So I'm going to visit the slides about Dijkstra algorithm in lecture 16. And just to remind everyone, Dijkstra algorithm is used to calculate the shortest or the most cost-effective path in a link state routing protocol. We talked about distance vector versus link state routing protocol. So the Dijkstra algorithm is one of the famous algorithms used in the link state. So it works by the algorithms the link state routing protocol works by collecting information from all nodes, building a database of link information. So each node says, I know about these links that I am directly attached to, and here is the cost, which could be any metric, could be delay, could be bandwidth, but here is the cost to using any of these links. And then they exchange information among themselves, the routers, and then each router will calculate the shortest path by itself. Right? So when we calculate the shortest path, the calculations for node 1 could be different from node 3, could be different from node 4. So we're going to practice going through this algorithm using node 1. Maybe we'll use a different node later. To do this, we need to use some parameters. So n represents the set of nodes in the network. So we have set of 6 routers in the network, right? S refers to the source node. T is, think of it as the intermediate set of nodes that we'll use to build our Dijkstra algorithm, to build the shortest path. And then the link cost from any two nodes, will refer to it as W of I and J. And the cost to the destination, so if we are in node 1 and we want to know what is the cost going to node 5, that's L of n which is the destination here. So what I will do in this recording is to go through how we got this schedule here, this table, right? And doing it by repeating the process step by step. So here I put the slide on top and I put the table here at the bottom. So initially, think of the node has all the information, right? It just needs to sort them out to figure out what is the shortest path to all other destinations. So it wants to know what is the shortest path to 2, what is the shortest path to 4, what is the shortest path to 6. So initially the algorithm starts by filling T, and in step 1 it fills T with one node, which is node 1 itself. If we are starting from node 3, the first node in the T set will be 3, but right now we're starting from 1. Okay, if I start with 1, node 1, what are the accessible nodes to it? What are the accessible routes or routers to it? So it turns out that we can access or we can reach node 2 with a cost of 2, and the path will be from 1 to 2 directly. I can reach node 3 with a cost of 5, and the path will be 1 to 3 directly. And I can reach 4 directly with a cost of 1, right? And the path will be 1 to 4. And I don't have a direct path to 5 yet. From 1, I don't have a direct path. So I'm going to leave this empty, right? I don't have information. Or you can represent it as infinity, like it's not reachable. So among these three links, which one is the short that has the least cost? Now, I highlighted the one with the least cost. It turns out it's the distance to node 4. So in my next step, I will add node 4 to my set T. And once I add node 4, now instead of looking at the distances from just one node, I have to look at the network from node 1 and 4. These two will form a new uh, alliance here. So the network will be seen from these two 4. So um, if I can go initially, I can go from 1 to 3 with a cost of 5, but now I added 4. Can I reach 3 in a better way? Well, turned out that I can reach 3 by going 1 to 4, 4 to 3 with a cost of 4. So I can update my net routing information here, and I can say 4, I can reach 3 by going from 1 to 4 and then from 4 to 3. And obviously I skipped 1 here. Why? So if I ask, or node 1 here ask itself the same thing, can I improve on the situation going from 1 to 2? Initially the cost was 2, and I can go directly. If I go 1 to 4, 4 to 2, will I have a better cost? No, I don't have a better cost because the cost will be 3 in this case. So I'm not going to touch this. I'm going to leave it as is. So now you can see among these two, my shortest path will be to node 2. But I haven't finished yet. So now, by adding node 4 to my network, I can reach 5, right? So I can, node 4 brings with it information about these 3 links, not just the link to 1. So now I have information about how to reach 5. So I can come here and I can say to reach 5, I can go to 4 first, and then I go to 5. So what is the total distance? Total distance is 2. And the path will be 1 to 4 and 4 to 5. Do I have a path to 6? No, so there's no change here. I will still, there's no change in the information. So now I have new information. I can reach 2 with a distance of 2. I can reach 4. I can reach 3 with a distance of 4. I can reach 4 with a distance of 1. And I can reach 5 with a distance of 2. Among all of these, I'll pick the one with the shortest path. So I have 2 here with the least cost, So I have 2 here that have the least cost. I can pick either the path to 2 or I can pick the path to 5. It doesn't matter which one. I'm just going to pick 2 here. So I am going to add 2 to my T. Right? And then I'll continue looking at the network from the new view here. So now I have these 2 or these 3 networks. 1, 2, these 3 routers, or nodes. So from these 3 routers, can I find better routes to the remaining destinations? What are the remaining destinations? 3, 5, and 6. These are the remaining. That's not included yet in my calculations. So I'm not gonna touch um, the column 2 because I already selected it and I put it in T. I'm not gonna touch the column 4 here because it's already been in the T. So I'm gonna look at 3, 5, and 6. Can I reach 3 in a in a in a better way on a least cost? Well, the original cost was through um, directly, and I rejected it and I replaced it with the cost of 4. But now with the intermediate node of 4. But now I can look at 2 and can say, can I go from 1 to 2, 2 to 3 in a better um, metric, better cost? Well, um, 1 to 2 cost me 2, and 2 to 3 cost me 5. Add 3 to 2 becomes 5, so it doesn't give me a better route. It seems like I cannot improve on this situation, can I? Not really, no change, right? How about does adding 2 improve the distance to 5? Also no. So in this situation, there is no improvement. So the information kept here the same, and here is the same, and I still don't have a direct path between the network 1, 2, and 4 to the 6. I don't have a direct path. Okay, but now I have 2 nodes. I have to add one of them to my T set here. So either node 3 or node 5. Node 5 has shortest or lowest cost. So I'm going to add it to my network T, right? And I have to look at the network now from the perspective of 1, 2, 4, and 5. So by adding this new node 5, can I reach 3 with a better cost than the original route? Well, if I go to 5 first, which is the path 1, 4, and 5, so the path to 5 is 1 to 4 to 5, so 1, 4, 5, that cost of 2. But from there I can go to 3 with a total cost of 3, which is better than the original cost here. So now, since I have a better cost, I need to update my route and say go to 1 to 4, then 4 to 5, then 5 to 3. Okay, also, now if I reach 5, I can reach 6. So now I can update my route here. I can say I can reach 6 by going 1 to 4, 4 to 5, 5 to 6 with a total cost of 4, and the path will be 1 to 4, 4 to 5, 5 to 6. Okay, now I have a choice to make. In my 5th iteration, I have to pick one of these nodes, node 3 or node 6, to add to my T. I will pick the one with the least cost. So now I can add 3 to my T set. And now my network will be including all but one node, which is 6. Okay, so now I picked this one. I have only one thing to update, which is the last path here. If you look from the picture here, I have two choices. I can go to 6 from 3, or I can go to 6 from 5, the original 5 here. Right? So the cost, when I added 3, I can reach 3 by going through 1, 4, 4, 5, 5, 3, and then 6, which will add 5 units of cost. It's not gonna help here. So I'm not going to change the path. So still remains to reach 6. I still have to go to the original path, which is 1 to 4, 4 to 5, 5 to 6. Now I don't have any more nodes to pick from. So I have the only thing that I'm left with is node 6. So I am going to add node 6 here to my network. And the outcome is the shortest path. So whatever left here is my shortest path. So if I want to go to 2, I can go directly. If I want to go to 3, I can go through 1, 4, 5, 3. If I want to go to 1, I can go directly. If I want to go to 5, I can go 1, 4, 5. And if I want to go to 6, I can go 1, 4, 5, 6. And this will be my routing table, right? I'm just going to remove the okay, I'm trying to remove the highlight here. It's not important, but just all right. So that will be my final outcome. This will be my routing table. The routing table will say here is my destination, and here is my next hub, and to reach destination 1, 2, 3, 4, 5, 6. So to reach 1, of course, that's self. To reach 2, I can go, the next hub will be 2 directly. To reach 3, I can go to 4. To reach 5, 4, I can go, the cost will be 2, and I can go to 4. And to reach 5, the cost will be 2, and I can go to 4. And to reach 6, the cost will be 4, and I can go to 4 there, right? And actually, the link state protocol will know the entire path, not just the next hop, like the distance vector. So it will know the entire path. And that's one example. We can repeat the same thing with another example just to go through it one more time. So I'm gonna pause for a second, copy this table, and then we'll do the same thing. Let's say by looking at node 3 instead of node 1. Okay. Okay, here we go. So I copied everything, but we're gonna do another example. So instead of starting from the source 1, we will start from the source 3, right? So we will assume that we are starting from this point and we are calculating the shortest path from the point of view of node 3. All right, so node 3 will do the same thing. We'll say I'm gonna start by including myself in the T set, and then I'll start looking, okay, if I have access to if I'm here, I have access to all of these nodes, right? So I can access node 2 with a cost of 6. Keep an eye on the direction there, right? And don't look at this because this is not relevant anymore. So I can reach 2 with a cost of 6, and the path will be 3 to 3 to 2, and I can reach of course myself shouldn't be included, so I should actually change the diagram a little bit, make it 1 2. Yeah, so I just copied it without changing anything. But of course, if you are starting from node 3, then the columns will be all but 3. So let me step back, and actually if you look at 3, it can reach all nodes, right? It has access to 1, it has access to 2, it has access to 4 and 5 and 6. So it can, in the first or all of them are immediate links from 3 perspective, but each one of them has a cost. So it can reach 1 with a cost of 5, and the path is direct 1 3 to 1, right? Actually the cost is 8 because it's bidirectional, and the cost going there is 8, not 5. How about 2? I can reach it with a cost of 6, and the path will be direct. And how about 4? I can reach it with the cost of 3, and the path is also straight. And I can reach 5 with the cost of 1, and the path will be from 3 to 5 directly. And I can reach 6 with the cost of 5, and the path is from 3 to 6 directly, right? So just to verify, I'm going from 3 to 1 with the cost of 1, and I'm going to 2 with the cost of 6, I'm going to 4 with the cost of 3, and to 5 with the cost of 1, and to 6 with the cost of 5. All right, among all of them, all these nodes, I have to look which one has the least cost. It turns out to be this one. It has the least cost. So I am going to add it to T here, and then my network will be seen from the perspective of these two. Okay, so now 3 will ask itself, or the algorithm will ask, can I reach uh, oh sorry, what I added is 5, not 1, so I added 5. The cost was 1, not the node, right? So, which is strange because I should have figured it early. 3 and 1 are not that, are not like they are directly connected, but the cost is higher. So if I look at this new node 3 and 5, from these two nodes, can I reach one with a better cost than the original? All right, so from 3 to 1, I have a cost of 8. But if I go from 3 to 5, I cannot reach 1. There is no connection between 5 and 1. So I cannot change this part. How about 2? Again, I can reach 2 directly here with a cost of 6, but when I added 5, 5 does not give me a better connection to 2 because it's not connected directly to it. So this part does not change. How about 4? Okay, 4, now I could use it, I could have connected to it, or I could connect to it directly with a cost of 3, but if I go to 5 first, I can connect to 4 with a total cost of 2. So I have a better path to it. That path will take me 3 to 5 and then add 4. How about 6? Initially, 3 can connect to 6 directly with a cost of 5, but if I add 5, I can go 3, 5, 5, 6 with a cost of just 3. So it's better distance. So now I can go 3, 5, 6. So from 3 to 5, notice the highlighted one here. So from 3 to 5, and then from 5 to 6, that will 3 to 5, 5 to 6, that will give me a total cost of 3 units here. All right, so in my new network here, or my